Hello, I hope that you're well, and I'm glad that you're here on my channel. Today, I'd like to share an interesting example that I use to help students understand the power rule, the product rule, and the chain rule all in one. So first, I'd like to do a little bit of review in one of my favorite colors, purple. That will be the power rule. Essentially, with the power rule, what we want to do is take the exponent, multiply that to the front, and then subtract 1 to the exponent. So for example, 5x cubed, the derivative of 5x cubed will be 3 times 5x to the 3 minus 1. So we subtract 1 from the exponent after we multiply it. So this is the same as 15x squared. Another example could be 13x squared. That's the same thing as 2 times 13, x to the 2 minus 1. With respect to x, of course, then we have this answer of 26, x to the first power. Usually, we don't need to write the first power because it's the exponential identity. So you could just say 26x, and that would be the same thing. This also works for negative powers and fractional powers. So you could say, for example, if you have the fifth root of x, that would be the same thing as x to the 1/5. The derivative of this is 1/5, because we multiply that exponent to the front, times x to the 1/5 minus 1. That's the same thing as 1/5 x to the negative 4/5. And so this would be the derivative of the fifth root of x. Okay, so I'm going to do another page that just helps us remember what the product rule is. Maybe I'll actually do this one in red. So the product rule is when you have a function times another function, and you want to take the derivative as a whole. So for example, if you had 3x times 7x, that's the same thing as 21x squared. If you did want to multiply that out, 3 times 7 is 21, x times x is x squared. So we know that the derivative of this should eventually be 42, because 2 times 21 is 42, x to the first power. Because they're the same functions, they should have the same derivatives. But let's use the product rule as it is. What we do is we assign one function to be called f. So I'll make that the 3x. And then the other function could be g. And then what we do is the derivative with respect to x of f times g is the same as f prime times g plus g prime times f. Prime here means the derivative of those individual functions. So the derivative of 3x is 3. So we would say f prime is 3. And the derivative of 7x is 7. And you could use the power rule there. For example, 7x to the first power, we multiply 1 to the front. That is 7x to the 0th power. And then x to the power of 0 is just 1. So a number to the power of 0 is just 1. And I'll probably make a fun little proof of that later. So I will say g prime is equal to 7. Now we have all the pieces that we need, because we know f, we know g, and we know their derivatives. So the derivative of 3x times 7x with respect to x should be f prime, which is 3, times g, which is 7x, plus g prime, which is 7, times f, which is 3x. And lovely news for us, that's 21x plus 21x. But what's this, my friend? It's 42x. So the same function should have the same derivative. Wonderful. So that's an example of the product rule. Lastly, I'm going to go over the chain rule before we do our most fun example. The chain rule, just so everyone can remember it, I will do it orange. Chain rule. It's like working on a chain. I like to think of it as like an oyster roll. Like you have a shell, and inside you have a fun little oyster. So the derivative of an inside function and an outside function is the derivative of the outside function times the derivative of the inside function. That sounds a little weird, so I'm going to write it. If you want to take the derivative of like u squared, for example, it would become 2u times u prime, where u is a function of x, or like a thing with x's in it. So for example, if you had 3x squared, and like u is 3x in this example, then we know that this function is really the same thing as 9x squared, because 3x times 3x is 9 times x squared. So the derivative, we know, I used the arrow for derivative, should be the same thing as 18x. Well, let's see this work. So 2 times the inside part, so that's 2 times 3x, times the derivative of the inside part. So the derivative of 3x is 3. Now, 2 times 3x is 9x. Yes, that's 6x. But then we take that 6x times 3, and we get 18x. So same function should have the same derivative. It does. So good news for us. The chain rule is you take the derivative of the shell, the outside part, times the derivative of the inside part. All right, so let's put them all together in my favorite example. And for this, I'll use my favorite color, which is probably dark red, fancy. Okay, so this fun example is actually a function that we'll be able to represent in 3 different ways and take 3 kinds of derivatives. So it will be 3x plus 2 squared. So I'd like to write this in a few different ways, and maybe you'll see where we're going with this. So first, I'll just keep the original way, and that will be 3x plus 2 squared. Then I'm going to write it, because this squared here means we take the number and we have it times itself, so there's 2 of them. So inside is 3x plus 2. We have 2 of those. So then that will be another way of writing this. And then finally, we could actually FOIL this out. So these are going to be 3 ways of writing the exact same thing. 3x times 3x is the same thing as 9x squared. 3x times 2 is 6x. We have 2 of those, so we have plus 6x equals plus 12x. And then 2 times 2 is 4, so we'll just add that at the end. So we have something pretty delightful. We have 3 different ways of writing the same exact function. So since they're the same function, we know that they should have the same derivative. Let's do the chain rule first. So what we do is we take the derivative of the shell, which is something squared. So let's represent that something, if you want it, with a u. U squared will have derivative with respect to u of 2u. Then we want to multiply by the derivative, since we actually want it with respect to x, of u prime. So here, we're going to take 3x plus 2 as our u. Then we know that we have the shell, which is that we're squaring something. When we square something that's like x squared, for example, the derivative is 2x. So we take 2, and instead of x, we'll write that original thing, the inside thing. So 2 times 3x plus 2. This is to the power of 1, because we subtract 1 from the exponent. Here we use the power rule on a larger thing. But because of the chain rule, we also multiply it by the derivative of that u, that inside thing. So the derivative of 3x plus 2 is 3. We don't need to write this 1 power, but then we know that we should end up with 6x plus 4 times 3. We'll distribute that 3 in as well to get a total of 18x plus 12. Excellent. And so this one is taking the derivative with the chain rule. Now let's do this one. This one looks fun, and then we'll do the product rule to finish. So this one is using the sum rule, which is something we didn't talk about, but it means if you take the derivative of like different terms and add them together, that would be the same as the sum of the derivatives. So 9x squared, that term becomes 18x to the power of 1. what does 12x become? The derivative of 12x is 12. So if you said that, great job. If you didn't say that, I don't know. So have fun anyhow. And the derivative of 4, because it's a constant, another rule we didn't talk about, but hopefully is useful, is 0. So the derivative of a constant is 0, and that's because the slope of like a flat line, the derivative is just the slope everywhere, is 0. So at any x value you put in, the slope is 0 of a constant. So like this is the line y equals 4, for example. Here's 4. The slope is 0. Okay, perfect. So we're already at a great place because actually we have 18x plus 12 again. So they're the same function. They should have the same derivative. So 18x plus 12 is how we'll end this. And now let's just double check with our cute little product rule. It's a little weird because we're defining f and g to be different functions, even though they're the same function, but that's okay. It works in general for any two things, continuous functions that you multiply together. So now let's take f prime, the derivative of f. In other words, the derivative of 3x plus 2. That's just 3x, 3, because this 3x term has a power of 1. We could use the power rule there. 3x to the first becomes 1 to the front, 1 times 3, x to the 0. So that's 3x to the 0. A number to the power of 0 is 1, so we don't have to write it. That's the multiplicative identity. And then we're done. We have f prime. Now let's find g prime as well. Since it's the same function, it should have the same derivative, 3. And so here is that again. The derivative of 3x plus 2 is indeed 3. So now for our product rule, we need f prime times g plus g prime times f. You could move these around a little bit because of the commutativity in that. So if you wanted to say g prime times f plus like even g f prime, that would also be right. So they're just, as long as it's an equivalent form, perfect, good to go. So then f prime times g is 3 times 3x plus 2. So let's write that. And then we add g prime, which is 3, times f, which is again 3x plus 2. So 3 times 3x plus 2. And wonderful news for us. This actually simplifies into 18x plus 12 because we can distribute in this 3 twice to get 9x plus 6 plus 9x plus 6. My friend, we have common terms. 9x plus 9x is 18x. And 6 plus 6 is 12. So, as you can see, these rules work together. They're friends with each other, and they don't contradict each other. They shouldn't, at least. A lot of these derivative problems have us using many rules, but it's also kind of nice because there's many ways to get it right. So hopefully this is interesting to you, and I hope you have a wonderful day. Bye-bye.